Good afternoon. My name is Neil Agarwal, and I'm excited to present Mowgli, Passively Learned Rate Control for Real-Time Video. This work was done with my colleagues Ray Pan and Ravi Netravali at Princeton University and Francis Yan at the University of Illinois, Urbana-Champaign. This work explores an alternative machine learning-based approach to improve video conferencing quality by leveraging historical telemetry logs that capture the behavior of the heuristic algorithm being used in production. Critical to the functionality of video conferencing is effectively adapting the rate of video streams over the network. And that's the job of a rate controller. It first characterizes network conditions based on recent transmissions, and then feeds that rate to a local video codec, which performs best effort compression on the fly on those raw video frames from the camera before sending it over the network. The goal here is to strike a balance. You want to maximize video bitrate for quality, you want to keep delays low for interactivity, and you want to avoid video freezes. Traditionally, algorithms like Google Congestion Control, or GCC, have handled this task. GCC is a hand-tuned, rule-based controller, and it's been designed to identify specific signals of congestion based on aggregate metrics around packet loss and packet delay. It's reactive, simple, and widely deployed. Now, in recent years, there's been growing interest in using machine learning, in particular reinforcement learning, to improve rate control. Unlike traditional rule-based approaches, RL learns through trial and error. An agent takes actions, receives feedback from the environment, and updates its policy to improve over time. Now, the promise here is that RL can produce smarter rate control policies by better leveraging rich telemetry signals and being able to reason over longer time horizons. Now, there have been two primary approaches to training RL-based rate controllers. The first is simulation-based training. Here, an RL agent learns within a simulated environment, and this approach is appealing because it's simpler. However, it suffers from what's known as the simulation to reality gap. It's difficult to build high-fidelity simulators that truly capture the complexity of real-world network dynamics. As a result, policies trained in simulation often fail to generalize and perform poorly when deployed in production. And this is a limitation demonstrated by prior work. Now, in response, more recent approaches have trained RL agents directly in production. These methods allow agents to interact with live conferencing sessions, exploring bitrate decisions in real time. And this has led to meaningful improvements. Prior work has shown that with enough interactions, RL is able to learn policies that outperform GCC in practice. But this comes at a cost. Because RL learns by exploring, trying out different actions, and observing what works, this process introduces quality degradations for real users during training. Poor bitrate decisions means real users experience real disruptions. So to better understand this, we trained an online RL agent and analyzed a representative session mid-training. In this plot, the gray shows the actual available bandwidth, and the blue line shows the bitrate selected by the RL policy. Now, ideally, the policy would closely track the available bandwidth, but what we see instead is aggressive exploration, significant overshooting and undershooting, causing quality instability for the user. More broadly, when we aggregate quality metrics across training, we find that video quality drops by up to 77%, and freeze rates increase up to 79% relative to GCC. These disruptions present a serious challenge for deploying online RL. So in this work, we consider an alternative approach. In particular, we start by asking the following question. What if we could learn a better rate control policy directly from existing logs completely offline, without ever having to interact with or impact real users? Our system, Mowgli, trains a better rate control policy by mining telemetry logs from GCC, the production heuristic. It uses offline reinforcement learning to generalize and improve upon GCC's behavior. And our experimental evaluation showed that it works. Mowgli is able to improve video bit rates by 15 to 39% and reduce video freeze rates by 60 to 100%, and nearly matches the performance of online RL without disrupting users during training. Now, before we go into the system designs and the training framework, I want to take a step back and discuss why this may even be possible in the first place. In the online RL case, we're able to generate wins from trying out new behavior and trying out different actions. How can we learn an improved rate policy from these GCC logs alone? Let's start with how we can model GCC behavior. In each trace, we can extract the following. First, the system state. This is made up of various telemetry and feedback signals, like delay, loss, and throughput. This is essentially all the information GCC had access to before it made its decision. We can see the target bit rate it selected. That is the update that GCC took. And finally, we can see the resulting quality of experience, which essentially captures the effect of taking that decision. And in our modeling, that's a function of received bit rate, the packet loss, and the packet delay. So we can represent these with the classic RL data modeling structure, sequences of states, actions, and rewards. Now from this data, we can imagine learning a decision-making policy that imitates GCC. Learn that given a state or a similar state, do the action that GCC took. But we want a policy that improves upon GCC. And the opportunity here lies in a key observation about the GCC behavior captured in the telemetry logs. From this data model, we observe that for key adaptation behaviors, like ramping up or ramping down the bit rate, GCC exhibits a variety of responses. For example, a key adaptation behavior is ramping up and quickly utilizing the available network bandwidth to maximize video quality. Here I plot examples of GCC's ramp up in different scenarios. The blue indicates the sending bit rate, and I overlay the computed reward. But what's different about these graphs is how quickly GCC is able to ramp up. The left plot shows GCC's more conservative ramp up, taking over 30 seconds to ramp up. The right plot shows GCC more aggressively ramping up, doing so in 5 seconds. Now we argue that this variety provides a learning opportunity because it shows how different rates of ramp up result in different average rewards. And a model in theory could learn to do better than GCC for the case on the left hand, let's say, by taking the behavior that results in higher reward for similar states and doing that more often. Now another key adaptation behavior is bandwidth drops, where we want to quickly detect congestion and drop the bit rate. Here are 2 examples of GCC's behavior in traces where the bandwidth drops. And these cases show a variety of how fast GCC is able to detect and react to a drop in bandwidth. In the left graph, GCC's reaction is a little bit more delayed, resulting in a steeper drop in video quality. And on the right-hand graph, GCC's reaction is a little bit more swift, resulting in a less steep drop in video quality. This variety exists to GCC's hard-coded behavior and being sensitive to various network signals for triggering congestion detection. Ultimately, this variety again provides a learning opportunity because it shows how different reaction times to, in this case, network congestion result in different average rewards. Now a model can learn to do better than GCC for bandwidth drops by observing the behavior that resulted in the higher relative reward and doing that more often. So what this means is that in order to improve upon GCC, we don't have to try out new actions or new behaviors. The key idea here is that for each of these adaptation scenarios, we can optimize over the variety in the logged responses and learn to keep and generalize the better behavior for any given situation. Now, with this in mind, let's discuss Mowgli's training framework. Mowgli uses the soft actor-critic method, a common RL method that trains 2 networks, the actor and the critic. The critic takes a state and action and estimates a value, essentially how good was taking this action at this given state. And this is a function of the reward over some time in the horizon. the actor ultimately decides what action to take given the state as input. And you can think that the critic ultimately provides a learning signal for the actor, guiding it towards selecting actions that optimize for the best behavior. We also incorporate conservative cue learning, an offline reinforcement learning technique. Because there's no ability to try out new data, there's a potential for extrapolation error that cannot be corrected. If the actor proposes an action that's far from anything GCC ever did, the critic's estimate becomes unreliable and may mislead the actor. CQL trains the critic to prefer actions from the dataset and downweight unseen actions. And in practice, this is achieved by adding a regularizer to the critic's loss function. We also incorporate distributional RL, which modifies the critic to predict a distribution over possible rewards, not just a single number. We find that this helps deal with variance in the environment, such as network behavior or downstream application effects. So this is the overall workflow of Mowgli. We start by processing existing GCC telemetry logs to produce trajectories of states, actions, and rewards. We train the policy offline, ship the trained model to clients where the model runs locally and replaces the GCC bitrate controller. We built Mowgli on top of WebRTC, an open source video conferencing platform. And because we didn't have access to a production testbed where we could collect logs and evaluate our own policies, we set up our own testbed where we considered both emulated networks and real cellular networks. For both of these setups, we ran GCC to collect a telemetry dataset that represents the existing logs during production setting. We trained on this data, and here are some highlights of our evaluation results. First, for emulated networks, we plot Mowgli's performance in green against GCC, the heuristic algorithm, in blue, on a number of key metrics: the average video bitrate, the percent of video freezes, and the frame rate. Across metrics, we find that Mowgli consistently delivers improvements over GCC. For example, Mowgli increases the average bitrate by 15 to 39% and decreases the video freeze rate by 60 to 100%. We further broke down these results to better understand where these wins are coming from. Here, for the same metrics and traces, we break down the results by the amount of dynamism in the bandwidth traces, as denoted by the x-axis, and compare the relative improvements. Here we observe that Mowgli achieves its largest wins over GCC in traces with higher bandwidth dynamism. And this is in line with our prior observation that GCC performs worse in more dynamic networks, and therefore these traces provide more opportunities to see improvements of a learned model. Next, let's revisit how Mowgli compares to online reinforcement learning, which, as we discussed earlier, has been a prior approach to improve real-time video rate control, but comes at the cost of significant user disruption during training. And here, we're specifically comparing Mowgli to the fully trained online RL model. That is the policy after convergence, once all the exploration is done. So now in the same graph from before, we include the online RL baseline in red, alongside Mowgli in green. And what we observe here is that Mowgli almost matches the improvements of the final online RL model. And this is a key result, because unlike RL, Mowgli never explores on users and never tries out new behavior and potentially degrades the quality of experience. It learns entirely offline using pre-collected data. So we're able to achieve almost comparable performance without the costly and invasive training process that online RL requires in production, providing an almost more practical middle ground. We also trained and evaluated Mowgli on real cellular networks across various cities in the United States on a variety of mobility scenarios. Here we plot the video bitrate for two different sets of cities. The blue indicates GCC and the green indicates Mowgli. And here we observe that Mowgli's wins over GCC extend to real cellular networks, improving video bit rates while achieving similar video freeze rates. So due to time, there are a number of aspects I was not able to chat about, and I refer you to the paper for more details on implementation, deployment considerations, limitations, and further evaluation results, including comparisons to alternate baselines and ablation studies. So the goal with this project was that we wanted to improve rate control for video conferencing. Now, prior work that leverages online reinforcement learning does this, but it requires invasive trial and error learning on real users by exploring various actions and alternate behaviors. In this project, we presented an alternative approach, mining GCC telemetry logs and stitching together high-reward adaptation behavior. In our experimental evaluation, we observed that Mowgli improves performance on emulated and real networks and nearly matches the performance of the online RL baseline. And I think looking ahead, there's a lot of interesting follow-up work. You could look at ways to combine both offline and online learning, or perhaps expand the logs we train on, incorporating both logs from production and simulation settings. And with that, thank you so much, and I'm happy to answer any questions.